Welcome back to Introduction to Software Reverse Engineering. In this module, we will explore bitwise operations and bit shifting. Welcome to Module 14. This module is focused on bitwise operations and bit shifting, both logical and arithmetic. In this module, I want to review bitwise operations such as AND and OR, which are used a lot when working with flags and sum enumerations. We will also explore logical and arithmetic bit shifting, both types, left shifts and right shifts, and corresponding assembly instructions. Let's start. Broadly speaking, bitwise operations can be divided into two groups: logical bitwise operations such as AND, OR, and NOT, and bit shifting, which includes logical and arithmetic bit shifting as well as bit rotation operations. Logical bitwise operations are very common when it comes to dealing with flags, enumerations, and in other multimedia applications and uses. Bit shifting has a swath of uses by itself and can be used in certain scenarios as alternatives to other operations. For example, a logical right shift by 1 can be used as an alternative to a division by 2 of an unsigned number. Logical bit shifting treats bits as a sequence of binary digits, filling vacant positions with zeros during shifts. This approach is ideal for unsigned integers or when working with bits as raw binary data. Arithmetic bit shifting is used for signed integers in 2's complement representation. When shifting right, the vacant positions are filled with the signed bit, preserving the number's sign. This approach ensures correct results when performing arithmetic operations on signed numbers. Fire up Ghidra and import bits.exe example program. Make sure to perform automatic analysis of the program before proceeding forward. Let's start with the example program shown on the screen. In this example, we will explore an array of values that was hard-coded into the binary as a list of values that are either individual flags or a combination of values concatenated with logical OR operator. Let's look into the compiled and decompiled versions of the function shown on the screen. First of all, note how static const array was moved out from the source code into the data section, and the function uses the array as if it was declared outside the function. Let's reconstruct the data and convert it into an array as it should be. Ghidra will suggest to create an array of 11 elements. This is incorrect. See the exit condition for the loop on line 17. Double-click on the memory address in the exit condition. It leads to a memory address below the 11th element of the array. Let's change the size of the array to correct one. Right-click on the array and select Data, choose Data Type Context Menu Element. The Data Type Chooser dialog will appear on the screen, showing the data type as an array of 11 elements. Change the data type to an array of 16 elements and click OK to apply the change. Once the change is applied, the array should look like this. It contains the values shown earlier in the source code with the values pre-calculated through logical OR operator. Now, let's inspect the format string function argument on line 15. The template is quite complicated. However, the function likes all the arguments to be used in such a template. To change the signature of the function, bring up Edit Function window as shown on the screen. Change the function signature to match that of printf, including the variable arguments checkbox. Click OK to apply the change. Once the printf function signature was applied, the rest of the function changed drastically. Ghidra pulled in previously hidden operations, given that the values became used in the body of the function. For example, a new block of code appeared, see lines 18 and 22, which drives use of true and false strings. In case of false, Ghidra successfully detected the string, but for true, it did not. The reason for this is that Ghidra's string detection is configured to detect strings 5 characters and longer. Therefore, shorter strings are usually go undetected. Change the data type of true to a string, as shown on the screen. With the change in place, the function looks properly decompiled in comparison to the original function we have seen earlier in this module. Now, let's take a look at the function that checks if the value contains the predefined bit flags, 21 hexadecimal in this case. The function's body is extremely simple. It employs bitwise AND operator to check if the input value contains the necessary bits set. Let's verify the decompiled code against the original source code. It is matching the source code exactly. Now, let's check another function. This one does a little bit more than check whether all necessary bits are set. That's a function called from line 16. This function is similar to the previous one. However, in addition to checking if all necessary bits are set, it converts the result to either true or false, 0 or 1 values. Let's check the original source code for this function. The ternary operator was removed by the compiler, given it produces the same result as the condition value itself. Before moving forward, note that Ghidra assigned bool as the return data type of the function. However, the assembly instructions operate on full 32-bit register values, EAX in this case, and not on AL. Because of this inconsistent typing, the caller function has Ghidra's internal concat bitwise function. The concat bitwise function is used by Ghidra in certain scenarios such as type mismatch and used CPU registers, or in some scenarios of bit shifting. In this particular case, see that the assembly has instruction test EAX, which compares 32-bit register value, whereas function return a bool value that should be only 1 byte and not 4. This prompts Ghidra to insert concat internal function to reconcile this discrepancy. Let's edit the function signature, its return type. Bring up the edit function window to change the function signature. Change the return type to an integer as shown on the screen. Click OK to apply the change. Once the change was applied, the concat function in the decompiled version of the function disappeared, given that assembly instructions match the expected data types. Now, let's change gears and look into bit shifting. See the top two functions on the screen. Left and right shifts apply to unsigned integer values. The decompiled third function that uses the first two functions is on the screen. It does all kinds of operations that we will skip in this module and focus on the bit shifting functions. Let's take a look at the left bit shifting. The left bit shifting function is on the screen. It generally matches the source code with one exception, an application of the 1f mask to param2 parameter. Note that the assembly instructions do not have that mask, but rather the shift instruction operates on CL register, the least significant 1 byte of the value. The right shift function is very similar to the left shift function. Now, let's take a look at the left and right shifting in application to signed integers. The caller function that uses the signed integers bit shifting functions is on the screen. Now, notice that the compiler combined left bit shifting functions for both signed and unsigned values, which is interesting in itself. However, the right shifting has its own function, where assembly instruction is SAR, an arithmetic right shift, which preserves the signed bit when shifting the rest of the bits to the right. The last example of this module is this function. It contains a single ternary operator that returns either 12,346 or 12,201 depending on the value of the parameter. Let's take a look at the caller function. Note that it employs modulo operator discussed in detail in Module 7. In this case, lines 14 through 17 is mod2 operation on a signed integer producing either 1 or 0 as a result. Let's take a look at the function with the ternary operator. This function looks extremely interesting, definitely not what you or I would expect from a rather simple ternary operator that returns one of two values that can be implemented with a simple if statement. Turns out this is rather common compile optimization to make sure that the code is executed linearly instead of having conditional branches. If you go through the mathematics of it, you will see that one of the values is hard-coded as in the original source code, while another one is the difference between the final value and the other available value. One of the reasons for such low-level code optimization is that generally executing linear code is faster than executing code that has conditional jumps. At least it was in the days before speculative code execution. In this module, we looked at and examined bitwise operators and the ways Ghidra decompiles them. We also looked at some other material covered in previous modules, which is a good way to refresh the knowledge. In the next module, we will look at switch statements. See you in the next video. If you are looking to dive deeper into software reverse engineering, I'd like to recommend my book, Software Reverse Engineering: Navigating x86 Windows Applications with Ghidra. This course draws heavily from the book's content. However, the book itself contains many more examples and insights that can help developing your reverse engineering skills. The book is available in both print and digital Kindle versions on Amazon, making it easy to access and read wherever you are. Additionally, the book covers subjects not discussed in this course, such as reverse engineering of C++ programs, classes, virtual functions, and more. I encourage you to check it out. Thank you so much for watching and learning with me today. If you found this video helpful, please hit that like button and subscribe for more content like this. Your support means a lot to me. If you have any questions or topic you'd like to discuss, leave a comment below or shoot me an email. I'm happy to chat. If you'd like to support me and the channel financially, you can do so through Ko-fi or Patreon. Links are in the description below. Thanks again for watching, and I will see you in the next video.